Okay. It's 5 p.m. Tomorrow is February 14th. And for those who have not found a table tomorrow, they are going out tonight. And I am one of them. All right, so I have to really get out of here at 7:20. Okay, that's why I'm asking for this sign-in sheet to be completely. So you give it to me at 7:20, and I'm out. Okay. All right. So what are we going to do today? Well, first we're going to start with assignment 2 presentation. Keep some notes. There's one minor addition that I need to do sometime tomorrow on the assignment. I'll explain what this is. So keep a note of that. Your assignment, the next assignment is titled Image to Video Semantic Retrieval via Object Detection. Okay, it is a task which is obviously a retrieval task, which is a kind of an important task. Having said that, there are no complications that will typically see a retrieval task like re-ranking models, nothing of that nature. The task here is almost too simple. Some of you may have gardening experience, so sometimes you come across a plant which you know. You take your smartphone out, you take a photo, and you say, okay, what on earth is this thing? And the semantic retrieval comes back with an answer. Okay? The same thing happens with your personal kind of photos. Sometimes they're asking you, is this what is this the name of this person? You say Nick, and therefore all these photos that are contain Nick, after that they are being tagged. So something similar is happening here, but it's slightly a bit more complicated. And goes as follows. We are going to give you a training data set that is over here. And together with a well-known object detector, our task here is not to develop an object detector from scratch, but just use an object. This object detector is capable of, or will be capable of, detecting parts of vehicles, the vehicle, as it is presented by a well-known YouTuber on that is doing car reviews. Okay, this is the vehicle. The video is pretty long. This is the part that I need to add tomorrow. It's like 45 minutes long. And right now in this assignment, we are focusing only on detecting exterior components, parts of the vehicle. Okay. So out of the 45 minutes, I didn't count it, but most likely something like 10 minutes will be spent on exterior kind of sort of presentation. And you will be using a tool called FFmpeg. Who has used FFmpeg before? Some people. Okay, so it's a well-known kind of tool to do all sorts of processing for videos, including, I'll double check that tomorrow, but including some kind of segmentation of that portion of the video that this guy goes around, okay, presenting the car. Okay. So out of the 45 minutes, most likely will end up after this step, which has not been specified, with something like 10, 15 minutes or something like that. Okay. All right, so now we have an input kind of video, and also we have a model that is able, for every frame that we are feeding into the model from the input video, to come back with, let's say, a JSON structure containing our detection. Our white hats are going to be in some JSON structure, and we are suggesting to you, not suggesting, we're telling you to make sure that all these detections end up in some kind of a Hugging Face data set in a Parquet file. Okay. Anyone who has used Parquet files before? One. Some people, okay. So Parquet files is almost like a de facto standard in dataset sort of efficient storage, retrieval, reading, and writes, if you like. And the reason why it is very efficient is because of its columnar sort of retrieval kind of almost like a vectorized way of retrieving this data. And it's being used also in computer vision quite extensively, apart from structured data. All right, so for those who do not know, the parquet is just basically a format that Hugging Face, for these reasons, automatically almost, no matter what the format you are sort of working on, automatically converts it to that format and allows you also to visualize. Now, okay, fair enough. We'll have effectively a video with detections in some format coming out. Okay. Any questions up to this moment in time? No question. Okay. Now we have the retrieval kind of task to implement. This retrieval task is going to be retrieving what? Clips. When I say a clip, what do I mean? A video clip. Few seconds duration. From this 10-minute, 15-minute kind of duration of the total video that you have, you're going to return back the 2 seconds, 3 seconds that are the specific components of the car. Let's say this guy at some point will go and present the headlamp of the vehicle. The object detector will say headlamp. If it says headlamp, you need to return back the corresponding clip that it is inside that kind of 15-minute kind of video. The clip is again 2 to 3 seconds. Any questions on what we are returning back? So the query images are stored in a Hugging Face dataset over here. I cannot click it right now because I'm in some kind of weird Cloudflare kind of arrangement. But if you click on it, for you, it will probably show some parquet file visualization. Okay? Some images will be on one column, some other metadata will be on some additional kind of columns. Most likely, some of you must have clicked that link. Okay. So for every row, we have a query image. A query image comes in, a video clip comes out. Some of the images are correlated. Some of the images are not correlated. It doesn't matter. Just return a video clip. Okay. Now, this is the full task definition. Follow this order, and you should be okay. The query images are not from the same video. They are from another car view, not a different model altogether, but a different video, again, presenting that vehicle. Any questions on this assignment? You know the deadline for this assignment. Did I post it? Right, the deadline? And I think that there's also, I heard there is a reprise-based kind of entry. And I will augment this assignment a little bit with this FFmpeg information sometime tomorrow. Okay. Okay, so that's fine. That's good.
So the video which we need to process, can we directly use a YouTube link, or do we have to download it first and then feed it to our model to process?
Yeah, you have to download it. Most likely you will need to use some kind of for detections. I think CPU is fine because we're not building a real-time system here, right? But you can just use it also, use Colab if you need to produce a detection that is. Okay? Yes. I'm deaf, I cannot hear you.
When will the grades for assignment 1 be released?
Good question. This is a very good question. I have no idea, but I'm asking them to post grades in some plus or minus 3 days, 1 week after the submission deadline. So this weekend, they most likely will grade. Okay. Any other questions? All right. So let's go now to finish, do some review of what we did last time, right? And last time we are already in week 4, right? We are already in week 4. And so last time I think I started discussing, I finished I think the maximum likelihood discussion last time. And I finished also the conditional kind of model. Both marginal models and conditional model was finished, and cross entropy was obtained at the end of this kind of discussion as a formula, right? And this formula is actually a very key formula, also known as log loss. And obviously, it has the connection of negative log likelihood, KL divergence, cross entropy. Okay, that connection was established, or this equivalence, I should say, was established. We, in other words, had, at least for the regression kind of problem, and later on for the classification problem, have the ability to return back our uncertainty together with our prediction. That was basically the discussion last week. And we did this classification kind of problem. And in this classification problem, we were satisfied, at least visually, that there is an optimal kind of threshold that minimizes the probability of making mistakes. We said that we are going to always make mistakes no matter what, because we have overlapping classes. Here there are just two. And so our job is to minimize the summation of these two counters. Okay. Are you okay? Any questions on this? All right. Everything is okay. Everyone is okay until they are not, which is probably discovered during the midterm. Okay, I'm just joking. All right, so the classification metrics. We had recall and precision, the two metrics. So we established also the trade-off between recall and precision, because there's a trade-off between false positives and false negatives if you follow that discussion with the histograms, right? And we finally developed started from the cross entropy general kind of formula at the top, and we specialized it when we have two classes. We call it binary cross entropy, and it was this kind of formula here at the end. And if we plot the per example loss, what is the per example loss? What is the per example loss? That's great. No one knows what is the per example loss. Come on. Did you watch the video again during the weekend? You have nothing else better to do than watch the video, of course. But what is the per example loss? What we had as, if someone asks you the per example loss in regression, what would you say it is? Per example loss. For each example, I'm paying a penalty. What is this penalty I'm paying? In the case of regression, we did it like lecture 1. Y hat I is my example, right? Minus yi, the whole thing squared. That is the per example penalty I'm paying for the regression problem, per example. In the case of classification, binary classification, how much I'm paying? That is my per example. This is what I'm plotting here. This is what I'm plotting here. And the shape of it led us to claim that the binary cross entropy as a whole, no surprises, obviously, that this entropy, this loss function has this structure over here, the 1 over m summation from I is equal to m, because obviously it has to convey the average risk, right, that we are paying, right, we are optimizing. This, per example, kind of loss is such that it analyzes carefully confident wrong decisions. That was basically our conclusion just before we started drafting now the binary classifier. And this binary classifier we drafted was a trivial kind of classifier. We call it generalized linear model. We are still in the linear kind of space, and it involved a linear sort of a unit over here, which is obviously the dot product, followed by a sigmoidal unit that played the role of compressing negative and greater than 1 numbers, allowing us to connect the y hat to what we call the posterior probability of what? Another question for you. What is the y hat at the output of a classifier? zero probability of
one.
the posterior probability of the positive flux. Okay. Silence. Now the torture is over because from that moment onwards, right, we will probably be dealing with a little bit more of a block diagram-y oriented kind of material, right, with neural networks and things like that. And life will be better. But unless we understand this stuff, I think there's going to be some problems understanding what really neural networks are doing. So spend some time on it because it's one and the same thing if you are using an LLM as a P model or it's just a simple thing like a binary classifier. At the end of the day, you have a gigantic classifier as a language model at the end of the day, right? So it's the same, exactly the same thing. Okay. Let's see. Did we go to demonstrate the single neuron in a binary classification task? No. Okay. So I'm going to start with some form of a small demo. I told you, for those who are interested to understand the block diagram, there is a YouTube video in my channel and explaining why the block diagram is the way it is, starting from the kind of the base rule. But let's continue a little bit now to see kind of anyway, I just want to quickly showcase a little bit what we have right now. What we have right now is we just drew really what we'll call from now on a single neuron, dot product followed by a sigmoidal nonlinearity. And we have how many features we have here? Two features, x1 and x2. Are you sure you didn't go through it? I did. Okay. That's what I thought. I asked and I said, okay, I'm losing my mind, obviously, so I did. We finished this discussion, was able to do it. Did we go here? Yes? Okay. So we persuade ourselves that this thing is not able to do it, right? And this is where we stopped, right? This is where we stopped. And now what we will do is we'll build a block diagram of this guy. Exactly the same binary classifier as it turns out, but obviously this classifier has more number of parameters. Similar stuff what we have done in regression. We're going to be introducing more of these parameters, but in a specific way, in a way that allows these individual kind of neurons to be connected together to form something at the output. Okay, so we need to understand that something and how this connected to what we have done earlier. It's kind of a mild block diagram kind of discussion. All right, so let's see. Today is the 13th. 213 E6. Lecture 4. All right, so let's see. I want to just draw the block diagram of what I have on the screen kind of earlier. So the same kind of X is coming in and is being fed to two neurons, one, followed two here, and the output of these two neurons go through neuron number 3 to form the white hat. That's exactly what we had in the screen a few moments ago. Now, it's customary for every neuron, if I actually put some kind of draw some kind of block over here, what a neuron is, have let's say a dot product and have an explicit bias addition, which is obviously a scalar, and have the nonlinear unit at the end. So this basically, this is the neuron. Either you see it this way, or you see it without this explicit class B over there. Please understand that the dot product can be rewritten to account for this class B. Okay, as you can do with even an x scalar, you can say x in our vector with 1x. And if you do a dot product, the first W0 will be called B. Right? But it's customary to just explicitly call it out as bias, the first term. So here we have three neurons. Two neurons are crossing the x. And the outputs of the neuron, which is basically y hat 1, I will call it y hat 1, and y hat 2, are entering a third neuron that combines them, uses them both. And each of these neurons is going to be associated with a parameter set of parameters. Right? So in the single neuron case that was completely incapable of doing the sort of finding it like this kind of decision boundary, the number of parameters, how many parameters we had? The single neuron case, which we did last week, how many parameters we had there? Well, we had two features plus the bias term, three. Okay, three, right? So three parameters. Now we have obviously 9 parameters. And these parameters are stacking up 9-dimensional W vector. Okay. The environment of this thing and the environment of what we have done last week is exactly the same. The output of the y hat over here, which I will call conveniently y hat 3, is going where it is going to go. What is the reasonable inlet for this y hat 3? If I am to train this thing and replicate what is happening if I press the play button, where is this y3 will go? To the loss function. There will be a binary cross entropy kind of loss. Someone will sit down and calculate the gradient of this binary cross entropy loss, and it will, together with the hyperparameters like learning rate and mini-batch size, which is also in the web interface that I just showed you, will result in a new W. Okay, that's basically the same thing, right? Same old thing that was happening. So I want to call this these two guys. Is y hat 1, what is the dimension of y hat 1? What is the dimension of y hat 1? No one knows what is the dimension of y hat 1. Okay, follow the diagram. You told me the dimension of x is how much? For this specific example that we saw on the website, the dimension of x was, you told me there are two features, right? So x is a two-dimensional vector. All right, this combination of this with 1 at the end is going to be three-dimensional, but at the end of the day, that any dot product over here will result into scalar. Therefore, the dimension of y hat here is a scalar. Therefore, the dimension of y hat 1 is a scalar, and two scalars together are going to populate a vector h, because I want to write the equation of this guy, right, as a usual dot product that I'm writing. All right, so for this kind of discussion, I will do a simplifying assumption and ignore, if you like, the bias. So what is the equation of y hat 3? What should I write? It is sigma of W3 transpose H. Do you agree? Okay, so it is equal to sigma of, what is W3? Has two components, W13, W23. Transpose H has two components, y hat 1, y hat 2, right? So this one will be sigma of W1, 3, y hat 1. I'm not doing anything intelligent here, just writing down what's happening in the block diagram. What I'm writing over here are called forward path equations, forward path equations. All right, so I'm going from the input to writing the output as a function of the input. Okay, so this one will be sigma of what? W1, 3. What is y hat 1? Sigma of W1 transpose X plus W2, 3 sigma of W2 transpose X. Oh, see. This is basically your y hat 3 expression. X is coming in, and y hat 3 is coming out. This thing is coming out. There are 3 observations that is worth making as far as this output is concerned. The first is that from the equation, we can understand the premise that this is a far more complicated hypothesis function. Remember, this thing that I just wrote is exactly equivalent to what we had as a polynomial in regression. This is your g of x comma w. This is your hypothesis function. This is what it does. So why this is more complicated? Well, than the single neuron we had before, because the single neuron had just one nonlinearity. Here we see nesting. So number one, we have nesting. Well, we have sigmoid of another sigmoid of whatever, right? So we have the first observation here. First observation is that we have nesting. In our hypothesis has some structure, in other words, it's nested sort of structure. Now, if you see though what is happening inside the big parenthesis over here, you'll come across something we have seen before, despite the fact it's not necessarily very evident. How can I call what is happening here? First of all, we see a combination. And it's a linear combination of what? It's a linear combination of this guy and this guy, some fraction of this guy. I'm adding it to another fraction of the other guy, right? And these are what? Features. Now remember, we were entitled to create features by hand. And we'll see exactly how, by doing so, we solve some problems. But over here, something different is happening. We do not have any manual involvement in the feature generation. And on top of that, we have, in other words, the network itself with what we will call from now on body of the network, generating the features for us, passing those features over to the head for each two. The head combines, and in the head, you will actually see what turns out to be a nonlinear function, but be very careful. This is the reason I'm actually drawing it by hand in this kind of trivial network. It has nothing to do with this guy. Very confusing. They are called sigma, and they, in fact, in this specific example, all of them are sigmoids. But very soon, this guy will be replaced. And when you replace, and you are free to replace this guy with yet another sigmoid. The question to you is, why the outer sigmoid cannot be replaced? Yes.
Because you want a probability distribution for classification.
because the outer sigmoid defines the task. You look at the output of the head to understand what the network is doing. So the moment you see a sigmoid here, what you would say the network is? Binary classification. If you see something else here, or if you see nothing here, which is my next question, you will say the task, different task. So the second point is that the body generates features and the head combines them. Now, this generation of features, the third point is that there is joint optimization of all of these W's. These W's are not independently changing. They are changing all together because the W vector that I'll call theta over here is the concatenation of all the parameters of all the neurons involved in the network. As you can see from the equation, the output is a function not only of the head, but also all the parameters of the whole network. So the features are in the features, right? If you imagine them as points in some kind of dimensional kind of space, during the training, the points are moving. The points are moving because the parameters are changing that drive these kind of features, phi1 and phi2. And they are moving in a direction such that the head will find this optimal combination, which is associated with W13, to combine them, in other words, in such a way that the classification task is successful with high probability for most of the test cases. So features are changing from the driver, which is basically the SGD, and the SGD is looking obviously at the loss and trying to minimize the test loss. So definitely we have this okay, which means that there is a sort of a joint optimization of all parameters. This trivial kind of network will soon be expanded and change kind of slightly. And the rationale of changing some of these nonlinearities there are going to be understood only after we go through elementary kind of backpropagation procedure to understand what's really happening during training. All right, so basically, if you press the play button, I don't know. Go to change the sigmoidal unit, but the inner nonlinearity there will be H here. Already you can see the more complicated kind of hypothesis, right? That is being at work. If you wait for a long period of time here, you will find some kind of new local minima, and most likely this kind of hypothesis will converge into forming the decision pattern. I don't know how long it will take, nor that I want to wait over here, but do this exercise at home, kind of, especially if you've never seen something like that in the past. Okay. Yes, question.
How how does neuron 1, 2 differ?
How neuron 1 and neuron 2?
Yeah, like what's different? Like they take
The difference is that they are forming different features from the same X. They are transforming X in different points in space. Because W1 and W2 are different from each other. Okay. All right, so from that kind of perspective, let's try to write down the general equation of what turns out to be called a dense layer or a fully connected kind of layer, and introduce some kind of discussion there with respect to the nonlinearity I told you will change. So in general, there's going to be some kind of architecture. We are going to have the body of the network consisting of more than one layer. Right here, the body of the network with just a single layer, stacking neurons. Now I'm going to draw what's happening when we have more than. Now instead of a square neuron, I convert it to a circle. It's easier to draw. So I'm feeding X to all of them at the input, right? This is my X. And let's say the second layer consists of 3 inputs, 3 neurons. The other layer from 2. And finally, in the head, I have a single thing coming out called Y hat. Now, we call it fully connected because we connect the output of these neurons, each of these neurons connected to all the inputs of the neurons above them. Now, I'm not going to draw the whole thing, of course, but you can get the idea. At some point, the body delivers whatever features, or also called representations, have been built to the head, and the head combines them in order to form whatever task it is to be formed. It could be a regression task, could be a classification task. So the Y hat over here will be produced at the output of some unit that is associated with this kind of task. Now, in binary classification, that unit will be sigmoid. The question for you is, if we are to go back to the regression example, and now we call it nonlinear regression, and I'm entitled to call it nonlinear regression because I have been using nonlinearities in the formulation of features, as I just told you. What should I see at the output of the network if I'm doing a regression problem? How can I detect that I now have a regression problem, not a classification problem?
Is the activation function.
There will be a linear activation function, some dot product that will give me the Y hat, will be a real number. I'm not going to see a sigmoid because, unless of course I'm dealing very specifically with some kind of regression problem that all the values of Y hat should be between 0 and 1. But for a house price, it isn't. So we'll see just a linear unit at the end. No nonlinearity will be present in the linear combination of features that is. Okay. So another thing what actually is happening here from the point of view of arriving to some sort of Y hat sampling prediction, as you can see, there is some kind of gradual sort of reduction in the number of neurons that are being used in each kind of layer. And the question is why you think that could be. Why you think gradual reduction? So what is really the reduction is actually telling us is that the number of dimensions of what I called H earlier, right? The representations, in other words, of X. Every layer builds a representation of X. This is your H1 vector, this is going to be your H2 vector, H3, and so on and so on. The dimensionality of these kind of vectors gradually, as you are trying to build kind of features, goes down. And the rationale of that is that in many problems, the X will be in a very high dimensional kind of space, but the essential componentry, which is needed for us to make a successful prediction, we live in a lower dimensional space. You can see that very easily in computer vision. Right now, if you take a picture of me, this pixel and this pixel have almost identical features, right? In other words, to detect me, or in your assignment, detect kind of something, you're not going to break me up into 1 million pixels. You will do the detection in a far reduced space, less space than the pixel level. You don't make predictions at pixel level. You make predictions at what is called manifolds, right? So you try to learn that manifold effectively in order to pick up the right representations in order to implement your task that you have at hand. So we'll see some examples in Python in a few moments. Okay, fine. So we have here the this kind of a triangular or pyramidal kind of structure. And let's write down what is going to happen now with in terms of an equation, because we cannot really draw everything. So we need to just define an equation for a single layer. And after we write an equation for a single layer, then we can start writing again the y hat as a nested function of that single layer equation. If you have multiple layers, you will be nesting for all these kind of layers to produce the y hat at the end. Okay. So let's write down the equation. So I'm going to represent a layer. Now you may notice this W now is a matrix. And I call it W1 because that's my first layer matrix. I will see now what this matrix is containing. Because now what comes out of this kind of thing is a vector. It's added to the bias vector. And what we'll be calling Z1 is fed to a nonlinearity called ReLU to form the vector H1. We need to write down the equation, which is now trivial kind of to write. The equation is, let me just draw also the ReLU function over here. This ReLU function is called rectified linear unit. And it's going to be a linear unit. In other words, this angle will be 45 degrees over zeta over z, and this is ReLU of z. Let me write it ReLU of z. And the function is definitely nonlinear. Why? Why ReLU is nonlinear function? Because it is doing clipping. It's clipping. Every positive number goes through unchanged, but what happens to the negative numbers? Zero. So the equation of ReLU is max of 0, z. That's the equation of ReLU. And therefore, the equation of the Fourier pass, if I may call it equations for the whole kind of layer, is z is equal to wx plus g. I'm not putting an underbar behind at the bottom of the matrices because they are already known that matrices are capital letters and they have multiple dimensions, so I don't have to overdo it. And then obviously h is equal to ReLU. And if my W is W1, they will be all decorated with 1, and the arc will be H1. This H1 now will become as input to the second layer instead of X to produce H2. H2 will go to the third layer as instead of H1 and will to produce H3. All the way up to the point I'm sick and tired of feature generation and I want to terminate everything. Okay, and I'm going to do that in the head. I'll combine all the features that someone gave me and match them, and this is a major function that the head is doing, do dimensionality matching. Right now, I have to produce a scalar. Therefore, I will combine everything to a scalar, down to a scalar. Sometimes, not to distant future when we are going to do multi-class classification, the number of dimensions that I need to go down to is, let's say, 10 or 20 or 1,000, whatever the number is. The head will do this dimensionality matching for me. Okay. So at the end of the day, I have to, as a designer of a neural network, to write down the dimensions in such a way that after many what is called projections, why I call it projections, why people are calling it projections, because it's exactly the same operation as you have a geometric projection. You have, let's say, this thing in a three-dimensional kind of space. When you project it to a two-dimensional space, you're doing a projection. It will be a point on the floor. You go from 3D down to 2D, a projection. Here you go from D dimensions for X, you go down to H1 dimensions on the features which are being generated in the first layer. Are we following what's happening? All right, so let's see now in terms of dimensions. I told you that we will be dealing with projections. And in fact, I'm entitled to call them nonlinear, right? Back in your machine learning course, what was your machine learning course before you come to this class? Called Introduction to Machine Learning. Okay. All right. In your Introduction to Machine Learning course, you did a linear projection. What was the name of the linear projection that you did? It's a classic, universal, very useful tool, linear projection. PCA. PCA. Principal Component Analysis. That was what they told you is the bread and butter of dimensionality reduction. Okay. All right. So trying to define the principal components of some kind of data set. Anyone has not heard about PCA before coming to this class? But I just want to understand what's happening. Okay, all right. Some people. Are you guys undergraduates? Yes. Okay. All right. All right. So that's fine. We'll see some elementary form of this PCA. Although I think also your assignment 1 must have hinted to some kind of a linear algebra kind of exploration in this thing, because the eigendecomposition of the covariance matrix, I think I mentioned that when I was presenting the assignment. I think I mentioned something about dimensionality reduction. So it shouldn't be too foreigner to you. But anyway, maybe you didn't associate that with the name PCA. Okay. All right. So let's see. Definitely, if I have the number of dimensions of the Z over here, and I have the number of dimensions of the X, what is the inequality I should write? NZ is greater than or equal to NX? Smaller than X. I'm doing projection, as I said. Remember the 3D to 2D projection. So NZ will be smaller than NX. Now, let's see in terms of dimensionality kind of matching, what the network is doing, what the layer is doing. So this is basically a single layer. Dense layer, as they call it. And why they call it dense, we'll see. Okay, it's a dense layer. Okay, so we we take this multiplication, right? Let me write it again. I'll write it again in terms of dimensions. Definitely Z is a vector, therefore I'm entitled to write NZ times 1 in terms of dimensions, right? I have equal to something, which is a matrix. X will be nx by 1, correct? Plus something else. Tell me what this should be and what this should be for this equation to be implemented and result into a vector of nz dimension.
NZ cross NX.
nz cross nx plus,
NZ cross NZ cross.
thank you. That's how we do the dimensionality matching. I want to do the projection, in other words. I want to go from nx dimensions down to nz dimensions. Now, a few moments ago, we had a neural network of 3 neurons over there, right? So let's have it in the notes. Anyway, let me do it by with my memory. So you have, let's take an example, nx to be 3 and z to be 2. Okay, let's do that slowly for the benefit of those who find this discussion difficult. Okay, but let's do it. Okay, so we have 3 dimensions going down to 2 dimensions. So okay, so I have here x to being what? x0, x1, and x2, right? And z to be z0, z1. Okay. All right, so it will be z0, z1 is equal to, you told me, 2 by 3, right? The matrix will be 2 by 3. 2 by 3, W0, 0, W01, W02, W10, W11, W12, correct? What is, oh no, yes, it is correct. X0, X1, X2, right? Plus whatever, B0, B1. Is this what the network is, then the layer will do? Okay, I didn't write the non-linearity. The non-linearity will be here, okay? Let me write it again because I forgot it. Value of this thing is going to be what? Z0, Z1. That's the equation of the layer.
Professor,
Yes.
if you do the ReLU on it, then wouldn't it be H1 and H2? H0, H1?
I will see, because the ReLU is applied element-wise.
Right, but isn't Z0 and Z1 like reactivation schools?
Yes, it is. If I do the ReLU, it will be there. It is, thank you. It will be H0, H1. H0, the output. Because over here I had C, but I didn't have the ReLU. The ReLU, which is a good point. Let me write it also what's happening here before we go to the specific example. So this is like an example. I didn't finish this dimension, so I have NH by 1 kind of vector would be the ReLU of N. I run out of space. I need to write in smaller letters, which is difficult. N H by 1 is equal to ReLU of what? N Z by 1, close parentheses. Which means that H1 will see what the first element of the input vector is, apply the ReLU, spit it out as the first element of H, right? Does it make any sense? Okay, ReLU, so we'll see that now in front of us, in fact. So let's see. It's going to be, who's going to do the brave, the difficult multiplication here? So it's going to be ReLU of what? W00, X0 plus W01 x1 plus W02 x2, right? Plus B0, correct? W10 x0 plus W11 x1 plus W12 x2 plus B1. Every single nonlinear function you come across, it will be applied element-wise, which means look at the first element of the here, apply a value to it. Look at the second element, apply a value to it. So nonlinear functions are vector in, vector output things, right? So this will be, from here I can conclude, H0 is going to be ReLU of this thing which I'm not going to write. And finally, H1 will be ReLU of this thing, which I'm not going to write. Are we following what's happening, right? So remember the discussion we had earlier. So it's a non-linear thing of a linear combination of features. That was the premise of the 3 neuron thing that was happening, right? But in the 3 neuron thing, we had also the 1 layer, so we had to terminate immediately, right? So right now we just have a feature generator here, a feature generator, non-linear combination of features from x0. Then the next layer over will be a ReLU of linear combinations of the feature of these features. We write down the equation. This is where the nesting is happening. And that's why gradually we are forming representations. We can, of course, but it's not performance-wise. You gradually need to go down in terms of dimensions. In other words, your network should have some depth in terms of, or height, as I call them over here, as I draw them over here, has some height, not just do one-shot representation learning, if you like, or feature generation. So I hope this trivial example, if you have a habit of reviewing what we're discussing in these kind of videos, should be enough to persuade you what exactly the projection is about. And now I am going to go now into Python to solve the problem of a network which is going to do multi-class classification. So we saw already the binary classification situation with a binary procedure, we know, and so on. And I want to solve the more general multi-class classification problem because there are some additional kind of components that I want to introduce there for the white hat now to stop being a scalar and in fact to be a vector itself. Okay. So I want you to go to that O'Reilly kind of library. Let's see. Let's go all the way to chapter 10 for 9. Yeah. Okay, here's your data set. So it's a kind of a data set of grayscale images. We do not know exactly how to process the images right now, but at least we will learn it in the next lecture. These images are primitive images, like 28 by 28 pixels only, and they are fashion items. It used to be hundred digits, but they're nowadays fashion items. And obviously, there are 10 categories over here. there are sneakers, dresses, whatever. Okay, and someone is asking you to build a neural network that it will, or an image that you've never seen before, it will classify it. So it will be a 10 class classifier. I'm going to be calling from now on the number of classes to be capital K. Okay, capital K will be 10. And I am going to draw a primitive network. Because I'm drawing it, I will limit the number of layers. But as I will go back to that Python code, we'll see the number of layers are, I think, 3 or 4. Okay. But I'm going to draw it to see what's happening. Okay, so the headline here is class classifier. Fully connected or dense architecture. You should be very familiar if someone gives you a problem such as this for your meter in English, how to convert the problem in English into a block diagram and dimension it. All the dimensions have to be clearly there in a block diagram, and also a justification of the dimensions. You should be able to justify in your mind why the dimensions are the way that you select. All right, so here's your input image. It is what is it? Or to be a handbag of some sort. Right, okay, so this is basically 28 by 28 pixels. Grayscale means that there's no color dimension here, just basically a matrix, right? At the input, 28 by 28. I'll be calling this matrix X prime. And I'm actually going to be drawing architecture where this X prime is coming in. And I'm going to create a vector out of the matrix. How? I think we discussed that already from lecture number 1. I'm going to flatten the matrix into a vector. How am I flattening the matrix? I'm taking the first row, append to it the second row, all the way down to 28th row. So now I have an X which has dimensions 784 by 1. It's a long vector. All right, so now I have the vector. And what I told you, the hypothesis that I'm building is going to be a neural network with a body and a head. So the body, for designing the body, I'm the designer. I need to specify the number of layers that I'm going to have. And I need to specify some kind of form of gradual projection, one layer after another, just like the pyramidal shape we had a few moments ago over there in the whiteboard. So because I'm lazy, I'm going to just do one layer, okay, for the body. So I'm going to hit the X with a well-known to you by now block diagram of a dense layer. I hope you recognize it. Here is your H1. Here is your B1. All of them are vectors. And I'm going in this layer, I am sort of deciding that the manifold that these fashion items leave as data points is in 128 dimensional space. Why 128 and not 256? You can have 256. There is trade-offs there. If you follow the rule of gradually going down in terms of dimensions, chances are that your manifold will be able to be trained and be found, in other words, be specified and found without really too much of a fuss. So here is your What happened to the Python code? No. This is a problem with this application. Here is the author of this network decided to do. Flattens very much to 784 or whatever, 784, yeah. Then the first layer has H1 of 300 by 1. Therefore, it has 300 neurons. If you remember the 3 by 3 to 2 projection, that's 300 neurons. Go back to that kind of projection. The number of neurons that you see here is how many? How many are the neurons you see? If you replace ReLU with a sigmoid, how many neurons you see here? 2. Of 2 equations, 2 neurons. The fact that I have a ReLU does not necessarily make it non-neuron. It is still a neuron, right? Okay, it's a non-linear function of the linear combination of features. Okay, goes to 300 from one project. This application is, these people are getting like $1 billion, whatever, from subscriptions. They are not able to just build a simple application. 784 down to 300. From 300 decides to go down to 100. Okay, I went down to 128 from 784 straight away because I just want to have a simple layer to do the projections. Mind you, he quotes over here the non-linearities he is using, ReLUs, right? And then it says, I'm done with features. And this is exactly the same thing I am going to say. I'm done now with features. This is my body over here. Let me add reduced. And I'm going to take whatever features the body created for me, 100 by 1 vectors, in other words, right? And I am going to decide how to combine them. And the question for you is, do I know what the head should produce at the output? We do know the number of dimensions. That's why I ask you, how many dimensions I need to produce at the output? Okay. K. So capital K is equal to 10. Remember, this was the fashion sort of items categories there. Okay, so I know exactly, in order for me to project from 128 down to K, what should be the dimensions of the W matrix, which I will call now W2. I made it too small. This is called H1, it is coming in, right? W2, H1. There will be some kind of bias, B2, right? And I have now Z2. This thing should be capital K by 1, which means that the bias vector should be capital K by 1. To add 2 vectors together. I hope I'm not confusing you. And therefore, the Z2 is going to be K by 1. This Z vector is also called logits from the logistic regression days. Okay. The logits are showing up here. So I have now 10 by 1 vector. But I need what for classification? I need a vector or I need something else? I need posterior probability distribution. In other words, while in the binary classification, I could get away with a y hat, which was a scalar between 0 and 1. Why I could get away with it? Because I had only two possibilities. If my y hat, which is the posterior probability of the positive class, is 0.8, then I know that the other bar that I need to define a two-bar posterior probability distribution is 0.2. Now I need 10 numbers. Being a posterior probability distribution, I will need to use something that I will call softmax to match, to create it. And this is going to be called y hat with underbar now. There is an underbar in this y hat because it's a vector. And this vector is k by 1. And let's see what's happened. Probability of y is equal to small letter k because k is the index of the classes, given x, comma, theta. Theta, you guessed it. Theta is W, all the trainable parameters. We need to count them also. Sometimes people ask you, how many trainable parameters do you have in the network? Okay, so W1, B1, W2, B2. This whole thing is going to be your vector theta. Obviously, W1 is a matrix, you flatten it to create a vector. So this large vector is we'll see now how large this is. But that's basically your variable parameters, which means that SGD will be working with this in this dimensional space to find the theta star. It is working in this dimensional space, doing the hard work in order for you, during inference, to do the projections with the theta stars and get your y hat posterior probability of the winning class and report it. See now how all this will unfold. So definitely I'm going to have a small letter k index over here, and I have 0, 1, 2, dot, 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 9. What I'm expecting to see as a probability distribution, I'm expecting to see a discrete probability distribution of 10 bars, right? So I'm expecting to see something like that. And at some index, I'm going to have the winning class. Before, to avoid kind of confusion, I only had 2 bars. This bar was called y hat, the other bar was called 1 minus y hat. Now I have 10 probabilities. For a probability distribution to be proper, what it should happen? The summation should sum to 1. You knew that all the way. Okay, so if I have this equation, I hope no one is surprised. From j is equal to 1, capital K, Pj is equal to 1.0. And so this guy over here, this softmax, has an equation which we need to understand why the equation is the way it is. Softmax of zk is equal to e to the power of zk summation over j e to the power of zj. Softmax, in other words, is a vector in, vector output function. Always receives 10 elements at the input, the 10 logits, converts that information to posterior probabilities at the output. That's all it does. It's a deterministic thing. No probabilistic information, but obviously has a specific structure as an equation And in order to understand it, I have a question. Remember the same form of ReLU. ReLU always produces positive numbers or zero at the output. This is the question for you. Given the structure, can Z2 be has any negative element inside it? Who said yes? Why?
Because even if Z is negative, then E, the power E is still positive.
I'm saying this is before the softmax. Is Z, what is the reason that Z may have a negative element inside it? Yes. So many people say no, it cannot. Many people say. And the reason why they say that is that, and they look at the ReLU, I'm getting a positive stream of numbers over here, or zero, right? There's a linear combination of positive numbers or zero, but obviously in this linear combination, many things can result into a negative number. Remember, there is no ReLU here. There's no ReLU behind the softmax. So can we have something that makes all the numbers positive, even if they have negative? And this is the role of the numerator display. Takes everything as a logic, positive or negative, into the power of Z, makes it positive. But obviously, it has to be normalized in such a way that the summation of these positive numbers with this denominator, the normalization is happening, sums up to 1. And this fully explains the equation behind the softmax. Another way to remember the softmax is to recall that the softmax looks like a softer version of something that we have already met called argmax. Remember what the argmax was doing in the maximum likelihood discussion? It was suggesting to you, go ahead and report to me, right? The best W you will find to maximize this kind of argument, right? So an argmax is something that says, okay, give me the maximum, forget about everything else, right? The softmax, it says, you know, I'm going to create a following kind of situation. If I assign probability of 0.8 here to this guy, right? This means that the summation of all the remaining 9 coefficients, right, 9 probabilities should be equal to 0.2. That's what softmax says. Right? However, one of these guys, in terms of probability, right, if it is slightly smaller than 0.8, just almost as equal in terms of class as this guy over there, right? This, which means that specific class, it almost like creates some kind of a competition between classes. So and this is the role of what the denominator is doing. Yes, doing this kind of normalization, but also creates some form of competitive situation. You cannot really assign, the confidence you assign to the winning class will be smaller than if this guy was all the way up here, just this guy, as compared to this one. This is very strange. So effectively, you are reporting reduced confidence, depending on obviously the heights of the other guys who didn't win the competition. And with that, let's see what happens. Of course. What happened to I was in the notebook, right? Who knows what happens? Where is the notebook now? Okay, most likely further down. Oh, here it is. Okay, so you can see we are terminating with a head of that has now 10 neurons with activation being softmax. We're producing now a posterior probability at the output. Have a y hat as a vector. And anyway, and here is the model summary. Model summary. This model summary is good because it highlights yet another thing. Dense layers are very expensive. We went from 9 parameters to 235,000 parameters. Why? Look at your notes, what we drew. Even with a single layer, went from 784 down to 128, right? What is the dense matrix W1 will have in terms of parameters? 784 by 128. How much is that? Several hundred thousands, or I don't know, 100,000, something like that, right? So 100,000 parameters just with one layer. Obviously, you need to add the bias, which is kind of small. Then from the 100, you go to 100, let's say in this case. Then for your W2 matrix here is 300 by 100 is how much? 30,000 plus the B2, which is 100. Here's your 30,100. So you sum this to this, and then finally you terminate. You terminate, you go from 100 down to 10. You pick up 1,000 plus 10, 1,010. Total 266,000 parameters, right? And to do the classification. SGD will do this operation, which means that the gradient has to be a vector of 266,000 elements long. Because SGD cannot work without the gradient. This is your theta vector, 266K. So now we need to understand how the gradient vector will be computed. Okay, that's besides the point. We'll spend some time on that in an efficient way. And finally, using the cross entropy and some kind of a training, blah, blah, and so on, we arrive at the desired point where we have a model of 260,000 parameters, and we are able to evaluate it over our test data set that we have never seen before. So we have a next test, this kind of matrix of several test kind of images. Here we have, let's say, 3 images that we are feeding into it. And we are using the .predict kind of API to feed these images to obtain a y hat, or that is now that has three y hat vectors. The first y hat vector, the second y hat vector is for the second image, the third y hat vector is for the third image. So we can actually go and see here who won the competition. K is equal to 9 won the competition here. K is equal to whatever won the competition there, and this guy won the competition in the third image. Behind this index, there is a category. Someone went and defined this kind of mapping from index to categories, and someone using this kind of mapping produced the indices that won the competition for the given x1, x2, and x3, the 3 images that we fed through the network. And we obtained this space. We always report the maximum, but at the same time, because the report the y hat, which is between 0 and 1, we effectively report the confidence that we have with respect to this thing. Okay, that's it. There is nothing else to it. It's too simple almost. Any questions? Yes.
That question going back to something earlier, but why do we use the rounded instead of the sigmoid? Most of them.
Yeah, that's a good question. Why on earth we are dropped this kind of sigmoid? And as we'll see in kind of a backpropagation discussion, where we have to calculate this kind of gradient, the derivatives of the sigmoid have really long tails, very long tails in saturation-wise. So it's like the derivative of sigmoid is sigmoid times 1 minus sigmoid. And this kind of derivative, they are not good news for gradient flow. Okay, so we'll see now how gradient flow completely dominates the discussion on how well the network can be trained and how we are able to correct the situation where we have some form of saturations going on because of the flow. In fact, we have to revisit in many instances architecture and devise new architectures to make sure that these gradients flow all the way from the output to the network, because we're going in the backward way, as we'll see, all the way to the input. Okay, so are we ready now to have this kind of discussion of backpropagation? Okay, so we are in the business now of estimating gradients. I hope you have reviewed some basics of calculus that I told you from when we did SGD, to actually go in the Khan Academy and review what is some basics of multivariate kind of calculus. And so I'm going to be dealing with a topic called backpropagation. And backpropagation is a procedure, which is very deterministic. In other words, there's no probability, there's nothing. It's just basically some kind of a procedure that has been with us for several decades. In fact, if you go back into the space exploration phase in the 60s and things like that, the people were very much interested and they're very much applying this type of backpropagation procedure by hand to estimate trajectories and finding, in other words, optimal sort of trajectories for the rockets and stuff like that. Right? In fact, there was a movie Netflix that if you haven't seen it, it shows in NASA there was this department called the calculators department. So this department was staffed by actual people who had this job title, and every single day they were coming in. They had these erasers and pencils, and they were doing these calculations. The movie that is Netflix telling you to watch is the movie that shows that the first Black woman who was a calculator in that department, which is unheard of at the time, made it to be in the engineering team. So that is, I can't remember the title of the movie, but it is if you GPT it or Google it, whatever, you will find the title. Okay, so these people were doing this, and so I will pretend that I am a calculator now. So I will do this operation of a very primitive kind of function that has only two parameters with backpropagation and calculate a gradient, which is obviously a vector 2 by 1. So the function goes as follows. F of x comma y is equal to x plus sigma of y, sigma of x plus x plus y squared. Okay, that is basically the function. And I'm asking you the following kind of question. Give me the gradient of f with respect to x comma y is equal to partial derivative of f with respect to x, partial derivative of f with respect to y. Hope no one is surprised by that question. Okay. So the first thing we need to do is to create what is called now, by the way, I'm also going to hear how I wrote it earlier. Sigma of x is given, but I'm not going to get into it, right? I'm not going to use this equation of sigma of x. I'm just going to treat it like what it will end up being called a gain. So the first thing that frameworks like PyTorch, TensorFlow, blah, blah, and so on are doing is they are creating, come up with an answer, they are creating a computational graph. So what is a computational graph? Okay, I have to open a parenthesis here, although I will delete it. I have this kind of concept of what's called a gate, which is an elementary operation that's operating on tensors. Tensors are generalizations of matrices. Okay, so if I have a volume, I can call it a tensor. Okay? Tensor can be called even matrices or even scalars. It doesn't really matter. It's just basically sort of multidimensional kind of quantities. So the graph is consists of a network of elementary gates. So the nodes of the graph are elementary operations such as addition, multiplication, division, and so on. And the edges are, over the edges, tensors will flow into the nodes. That's why the tool was called TensorFlow at the moment. So I have in the edges going to be tensors, and the nodes will be computations, okay, elementary computations. That is basically the computational graph will be. And now I'm going to start drawing the computational graph, which will take at the input the arguments x, y, which are tensors in general, and at the output will produce f. How? In order to keep the premise of elementary kind of gates, I'm going to build the elements of the function and calculate them gradually. Okay. That's a key requirement for backpropagation to work, as we'll see. All right, so I will do that. So let me delete this thing. So I'm going to start from the very bottom of this kind of page over here. And I am going to have the two input tensors. And just kind of draw with me. So X tensor and the Y tensor are coming in into the gate class, we're doing the addition. So I'm calling I need to name the output tensors as well, as if they are Python variables. So I'm naming the output tensor XPY. You can name it whatever you like, but I just want to name it in a way that kind of conveys the meanings of the operation of the gate. That's the reason why I call it XPY, X plus Y in other words. Okay, so XPY tensor is formed. I can see that I need also a squaring operation because I'm in the denominator land. So I'm going to call it XPY SQR, the output kind of tensor. I know that I need to sum to that some form of sigma of x. So I'm going to I'm not going to expand sigma of x. Add sigma of x to what? This guy. And I'm entitled to call it the tensor denom, which is my denominator. As you can see from the function. Take x and sigma of y and add them together to form the numerator. And then I'm going to take the denominator, invert it, and I'm going to call this in the norm for this region. And I'm going to multiply finally these two, right, to obtain f. Yes.
Are the sigma of x, sigma of y, like the same sigma function?
Same sigmoid, yes. Not same sigmoid, the same function. to differentiate. So I hope you're persuaded that this computational graph gradually calculates f. Okay. So backpropagation will have two passes, as we call them. The one pass is the forward pass. That goes from the input to the output, and the other is the backward pass. That goes from the output back to the input. So I'm going to start writing down now what each pass is doing, and I will support it with the necessary kind of equations. So the first equation, the first pass is forward pass. Okay, first equation. Now, the only requirement I have for this kind of computation of the forward kind of pass is obviously I need to start from somewhere and arrive at the end on f is equal to something. And that something should be a previous step of calculation. And that previous step of calculation should be another, two levels up previous step of calculation. So I'm gradually calculating f, right? Just like what the computational graph is telling me to do. So I have, I can start with x and y, sum them together, right? I can start from here because there's absolutely no previous requirement. Someone is giving me values of x and y as arguments, and it's telling me if you wiggle these two, how much your function changes. That's basically the question, right? Okay, so I can also start from calculating sigma of y, and I can also start from calculating sigma of x. There is no dependency, in other words, on any of these three choices on previous calculations. Obviously, I cannot start from here. So in my notes, I have started from sig y. And I'm going to write it down. If you start from sig x, if you start from x plus y, you arrive at exactly the same thing. This is equation 1. Nu is equal to x plus sig y. Notice that I didn't write x plus 1 over 1 plus e to the minus y. I reduced the fact that I already have computed the sig y. There is a memory that contains the value of sig y here because I computed this step 1. Just retrieving it like pointer, do the calculations here. Store that into another memory. Sig x is equal to 1 over 1 plus e to the minus x. That's equation 3. Xpy is equal to x plus y. That's equation 4. Xpy S2r is equal to xpy times xpy. That's equation 5. I'm doing trivial things. I hope you recognize them. The norm is equal to sig x plus xpy sqr. That's equation 6. If the norm, the tensor is 1 over the norm, that's equation 7. And finally, f is equal to nu times in the norm. That's equation 8, and I'm done. I'm done with the forward pass. I have now the f as a number stored somewhere. Are you following what's going on? Okay, gradually I calculated f. Forward pass is the easiest thing in the world. That's why when someone is giving you a backpropagation question in an exam, they will assign 2 points in the forward pass and 8 points on the backward pass. All right, so let's see what's happening in the backward pass. In the backward pass, I'm going to start from the top of the diagram. And here's the big picture. I was given an equation which connects the output and the input. I will call this the global problem. In the backward pass, I will convert the global problem into a calculation. I will need to respond back to the question, obviously, at the end. But I'm going to respond to this question gradually, just like I did it in the forward pass gradually. I'm going to do it in the backward pass gradually. At every step of the way, I'm going to solve a local problem that only depends on the gain that I'm dealing with at that moment in time. And then magically, when I'm done with this process, I will arrive at the solution of the global problem. But as I said, connects X and F because it is asking the question if you change the slightly the anyway, if you change slightly the X and Y, how much the F will change? Is everyone following the big picture? Yeah. Yes, they have to invent also get some funds from what's called the manufacturer of tuna or something like that. Famous manufacturer of funds in PCs, in Workstation. Okay, so let's see. I want to start from the top and I'm going to apply a template as I'm going and visiting every gate. I'm going to draw the template right here. Doesn't matter if it is in the section of the forward pass. The template is here. I'm going to have, in general, a gate G that was in the forward pass from processing tensors in general X and Y, produce tensor Z. Because that was basically what I see every time in the forward kind of pass. In the backward pass, I'm going to receive what is called an upstream gradient. Upstream gradient. And upstream, I call it upstream because it comes from above. It is not my responsibility to calculate it. Someone will give it to me. And I am going to calculate, however, two downstream gradients. In other words, two gradients that are going to flow over the input tensor edges. The downstream gradients will end up being upstream gradients for somebody else later, as you can imagine. And I'm going to apply the following template for the calculation. The downstream gradient is going to be the upstream gradient, partial derivative of G with respect to X. Downstream gradient is going to be the upstream gradient, partial derivative of G with respect to Y. This template has a name, it's called a chain rule calculus. And we'll see how it's going to be applied now, starting from the top, where about the diagram, and how I will gradually apply it. Obviously, I'm not going to do the whole exercise. I'm going to back propagate, as we call it, let's say 2-3 gates, and then I will leave it up to you to finish the task. So over here, I told you that someone will give me an upstream gradient. However, at the very beginning of this kind of process, I notice that the downstream gradient is trivial to calculate, the df, whatever name I have given to the tensor in the forward pass, I will add a small letter d in front to name the tensor the downstream gradient in the backward pass as a convention. I forgot to name the sig y, the sig x. Okay. All right. So what is df? The first is partial derivative of f with respect to f. How much is this? 1. Now I'm going backwards. This means I now need to go in a deterministic way. Backward migrate equation 8, then 7, then 6, 5, and so on. I'm not going to change in the order at all. So let's backward migrate the first equation. Obviously, I have now my upstream gradient, and I need to calculate these two downstream gradients. The gradient names is d num, and the other one is d in the num. Whatever this is, ed with d in the num. Okay. So let's apply the template. Okay. D num is equal to, what is the upstream gradient? df, partial derivative of g. What is the gate is doing? Is doing a multiplication. Who is going to tell me the multiplication operation? Equation 8 of the forward pass. So equation 8 of the forward pass is telling me num, that's great. Decline. What happened? The meeting is being recorded. Okay. Are we still here? We are still here. What was doing? I was doing num times in the num, right? Respect to what? Question for respect to what? You answer while I'm going to text someone. Okay. You answer the question? Sorry, I need to check the back again. Because the only reason that I received 2 calls. Okay. I need to transfer some money. Give me 1 minute. Okay. Seems that university students are starving. It's a point. All right. So what I was asking you a question. What was the question? The template with respect to what? With respect to the port, right? That we are calculating this tensor with respect to, in other words, num, numerator. Okay, who is going to give me the answer? Now, I told you there's a lookup table in the calculus review page. Lookup table of primitive derivatives, right? You are entitled to print this lookup table and have it with you in an exam. Okay. In this lookup table, you're not going to see any equation like this, but you're going to see x's and some kind of scalars multiplied by x's and things like that, right? So you're going to see something like partial derivative of a times x with respect to x. X here is your num. Something not numerator is going to be called a or c or whatever, right? So the answer to this from the lookup table is yes, in the num. Again, what I have done to open a parenthesis is I have looked up where is this lookup thing going on. Where's the website? So in your courses, sorry, books, prerequisites, calculus, table of simple derivatives. Which entry in the table have I just used? Let's go. So I have f is x in our case, right? So I have a partial derivative of c times x with respect to x, and therefore it is c times partial derivative of x with respect to x, which is 1. Therefore, the answer is in the num. So is everyone following that? I hope everything was clear. Okay, so let's keep this table handy. Let's do one more. So I had to just use this entry, partial derivative of a times x with respect to x, and the answer is a. Where are we going next? We have backpropagated equation 8. No, we haven't, because the gate, the top gate over there has 2 ports. We backpropagated 1 port, we need to backpropagate the other port. Don't forget that. So we have to calculate the d inf the num. Exactly similar, analogous operation of calculation will happen, and the d, which is called inf the num, is going to end up being what? No. We are done with 8. We have 2 downstream gradients. As I told you, each of these 2 downstream gradients will be upstream gradient for another gate that follows. Okay. What follows though? Follows 7. You cannot go to 6. Go to 7. You have to go to 7. 7, what gate is 7 in the diagram? This guy over here. So it receives an upstream gradient and it produces a downstream gradient. What is the name of the downstream gradient tensor which I need to use? D the num. Okay. So I have used that. Okay, I have written this down. Okay, so let's do that. Okay, so I'm doing now equation 7, and I'm going to stop soon. Equation 7. In equation 7, I see just 1 port. So I'm writing D the num is the upstream gradient, which is D inf the num, right? Times what? partial derivative of the function that the gate is implementing. What is a function? 1 over NO with respect to what? The NO, right? So if I go to this lookup table, I know this, I have already calculated this. That is definitely one thing I want to refer to in the future when I'm trying to explain where the benefits of propagation are coming from. But here I need to go back to the lookup table. Which gate should I use for this? Which gate should I use for this? The last one. This guy over here. I have to use this guy. If f is simply x, right? The partial derivative of 1 over x is minus 1 over x squared. Okay. So this is equal to num times minus 1 over the num squared. That's it. Equation 7 is done. And if you progress, you go to equation 6, and so on and so on and so on. And I will draw what's going to happen. Equation 7. Equation 6 is what gate? Is sig x, this guy. So you will get to compute this guy and this guy, and then this guy's. At some point you will come here. And finally, at the very end, you will have to calculate downstream gradients that are these arrows. These are your solution. These arrows are your solution. There will be a dx and dy. But dx and dy, if you go back to your notes, there is an equation at the top right corner. Are the elements of the gradient vector. Be very careful of these points. There are 3 points. These are hidden gates. You treat gradient flow that flows from the top of the network, goes down. The analogy is treated like water. At every point, there is a valve. Something is happening to the water flow. There is some kind of diversion. There is some form of attenuation or amplification, doesn't really matter. But over here, these are called fork gates, and the water's flows will sum together to do the propagation of these gates. If you see their website, I want you to go and propagate 65432 at home and look at the website in terms of the solution. The solution is we did this together and this just now. You probably noticed what I just mentioned. This plus equal thing. This plus equal thing is because of gradients arriving at these junctions and they are being added to produce a downstream gradient. For the x, there are 2 points of addition. For the y, only 1 point. As you can see from the diagram, this is the first point of addition, the second point of addition with respect to x. And for the y, there's only one junction over here. But the right solution will involve the addition of the downstream gradients of those. And the rationale of that is explained in your notes. The backpropagation of all these kind of elementary gates. Which of course, for those who have followed, begs the following kind of question. Why we have what's the point? Why we believe that this kind of operation we just described to break this kind of global problem into a chain of elementary kind of problems or local problems is of any value. So the first reason is that, as you probably noticed from just 2 gates that we backpropagated, we are reducing earlier results. So another result that we had earlier is being reduced. For example, this guy was involved in the local calculation of another gate that followed from the forward paths. Because the second reason is that we insisted of making these gates elementary. And the elementary nature of the gates buys us something quite important. The local gradient, downstream gradient calculation, which was the only operation we had to do, can be symbolically expressed. Just like when I was looking up a lookup table, I was telling you what is the solution. We can actually go and say, okay, if I have a downstream gradient, what is the function that will produce an upstream gradient? What is the function for that specific gate and other that it will produce a downstream gradient? That function, it's symbolically pre-calculated. Here's your solution. I'm not doing anything for that symbolically calculatable gains. And the most important reason is that all of these local calculations, which can be symbolically themselves calculated, they can be massively parallelized. Why? Because if I have a gate over here, the dependencies of calculations of the downstream gradient for that kind of gate is local. That's why we call it local problem. Have probably no touch points, if you like, to another gate far away from the network. So I can parallelize this operation. I can do the log calculation of an independent gate. I can find out what are the independent, parallelize them, and all the log calculations are actually happening in parallel. So 3 reasons why backpropagation works. And now you're going to say, okay, fine, but these things do not really look like neural networks. Okay? But we did this exercise to do it by hand to understand the elements of that kind of justification, which kind of merit. In your website over here, I have this kind of section that dark mode is when you're in bed reading the website, but this mode is, I think, better for projectors. Okay, so in the same way as we have gates which are an addition, and multiplication and inversion and things like that at the scalar level, right? We have gates which are typically met in neural networks. For example, in the dense neural network, we just did the dense kind of layer. You had a matrix by vector multiplication. Is this the first time that someone meets a matrix by vector multiplication in a backpropagation way? No, we can symbolically calculate what will happen. And this is basically what happens here. We said, okay, tell me the partial derivative of the output of the maximum multiplication with respect to, let's say, the input x. It is this guy. You don't have to calculate it in the way I did. You just pick it up from the lookup table. Just like this lookup table is very dedicated to the neural network type of constructs that we are going to meet. Probably you remember at some point in this kind of lecture, we had something like that. Not only we can do gate by gate, even though this gate could be matrices, vectors, things like that, but also we can actually go and deal with composition of gates that are typically met in neural networks. Like, for example, over here I have a loss function at the output of the cross entropy, and I want to calculate the gradient, the downstream gradient, over this side that will go down into this matrix by vector multiplication. And the solution is right here. Take your y hat that you're going to get over here, subtract from it the y, and you are done. That's your DZ. And from your DZ, you can go and, further down whatever gates you meet and things like that. Okay. So symbolic calculation is a big thing. And all is going to be happening once you have your formulas, you have parallelism, and you have reuse of early results. And this thing is the reason why we can actually afford to actually do the 266,000 parameter gradient calculation fairly efficiently. So if you run it in a GPU, obviously the training should not be too much of an issue with these days. It used to be a very big issue many years ago. Okay, any questions on backpropagation? All right. Okay. Over here, to close a little bit the discussion. Over here, I have some exercises on, let's say, backpropagating a single neuron. Okay, backpropagating a single neuron. So it looks horrible, and it is. Well, I'm joking, or it's not. What I want you to do is, until next time we meet, backpropagate just the function I just gave you, right? And then go and read a little bit the formulas which I have just presented of elementary kind of things. Like there are two references which I think is worth printing out in this backpropagation in DNN. This reference, this is, tell me that it works, okay. This references, I provided the formulas, right, the symbolic formulas, right, at the end of this kind of lookup table. But for those who have nothing better to do, there is a justification why the formulas are the way they are from this kind of paper. So when you have a matrix by Bernoulli multiplication and you wonder why on earth the result is like this, the justification is here, right? So for all the gates I wrote down, the results are contained here, right? So dimensionalities are obviously increasing now to gradients, and in the next dimension up we call it Jacobians, but the principle stays exactly the same. So I will start the review of backpropagation from that single neuron backpropagation example next time. So we are perfect. So I just wanted to review though, don't sort of spend the weekend, which is it, are you working on Monday or is the university closed?
It's closed.
The university is closed. So you have a very long weekend. Just, watch a video or two or something like that. And just make sure you know the basics of what we discussed today. And next time I'm going to start the review with a single neuron backpropagation to just prove their point that it's not really something to be afraid of. And I will enter the discussion next week with networks which are able to process images. They are called convolutional neural networks. And from there, we will propagate down to object detection at some point before your final midterm exam, I think, or we'll see how. Okay. All right, thank you. And I will talk to you in next week. Start the assignment. That's the key. Start it. Don't wait the weekend before or the 1 hour before. That is lunch. Yes, yes, you need to open the ticket now. And in the ticket, we'll agree on the time we are going to meet. And then you need to send me in my calendar Gmeet. All I need to do is just press the link.
So even if it's for some personal guidance or how to approach things, questions, I can. Thank you very much.
Don't forget to sign in. There is OCR software processing these pages. write in a good way to recognize.